graphs look like. So here are a graph of all of the radial wave functions. All right. And so right here is my 1s orbital. This just decaying exponential. Okay. When we look at n is equal to 2, L is equal to 0, here's my 2s. And let's just keep going with that. N equals 3, L is equal to 0. Here's my 3s. And now n is 2, L is 1. Aha, that's my 2p. Okay. N is 3, L is 1. There's my 3p. And n is 3, L is 2. That's my 3d. Okay. So what about nodes? Well, let's highlight here specifically where this crosses 0. Okay. We already remember that our total nodes was given by the particle in the box problem, and that's n minus 1. Okay. So if we now start to kind of play with that, right, when we look at the 1s orbital, we see 0 nodes, and that makes sense because 1 minus 1 is 0. Fantastic. What about 2s? Okay, well, if I look at where this crosses right here, okay, look, there is 1 node. So we can see with 2s, let's just tab these down, right? So 1 minus 1 equals 0. And so now over here, 2 minus 1 equals 1. So there's our node, all right? So let's just keep going this with 3s. Now I know maybe my marker just covered it up, but there are 2 nodes. There they are, okay? And so that goes as, let's see, 3 minus 1 equals 2. But now when we go to 2p, because it's n is equal to 2, we should expect to see 1 node, but there's 0 nodes in there, okay? And then similarly with 3p, if you look at this now, there's only 1 node, but maybe we expect it to be 2, okay? So as it turns out now, we have total nodes, and we also have this thing called radial nodes. And so the radial nodes are only observable on the radial wave functions, okay? So radial nodes actually goes as n minus L minus 1. And so now if we go to this 2p situation, my n is equal to 2, my L is equal to 1, minus 1 equals 0. Okay, 0 nodes. And so same with 3p now. We have a 3 minus 1 minus 1, and that's going to equal 1. So 1 radial node. And then now with 3d, right, it's 3 minus 2 minus 1 equals 0, so 0 radial nodes. Okay. So now how do we connect the total nodes and the radial nodes? Well, the last type of node we have is called an angular node. And just to remind you, right, nodes are regions where the wave function equals 0. So that's where we expect the electron to not exist. Okay. So we're not going to observe angular nodes on this radial profile. We have to look at the theta phi YLM spherical harmonics, right? We have to look at the full three-dimensional picture to get the angular nodes. But as it turns out, angular nodes are total minus radial. Okay? So, for example, let's see, are there any here? So these are all showing me pretty good stuff. Aha, so let's talk about 3D for just a second, right? So we got 0 radial nodes, okay? Except for the fact that it's n is equal to 3, it should have 2 total nodes, the 3D. But now we can recognize because it's 0 radial nodes, we know that 3D will have to have 2 angular nodes. And we're going to have to observe those on an angular graph. Okay. Same with the 2p, right? There's 0 radial nodes, but there should be 1 total node because its n is equal to 2. So that means 2p only has 1 angular node. 3p is going to have 1 angular node and 1 radial node, etc. Okay. So let's keep moving forward with that. And now let's put together our full 1s wave function. Okay, so my nomenclature is going to go as follows. I'm going to write it as psi 1 0 0, and so that stands for I'll write that up here. So psi n l ml. That's how we're going to put together our total wave function. All right, and so I know that I can break that up into r of 1, 0, right? R of NL. And I can also then break that up because I know that Y is, YLML. So that's going to be Y 0, 0 of theta and phi. Okay? And just to remind you, right? In this chapter, we spent a lot of time, that whole first lecture, just developing this radial wave function. In chapter 8, we already came up with these angular wave functions, the rotational, right, wave function, the spherical harmonic, that satisfies our rotational component. We've already done it, right? And if you recall, I gave you this big table of spherical harmonics. So here I'm just kind of zooming in on the shortcut here. And so if I put this together now, right, I'm going to say psi 1, 0, 0 as a function of r, theta, and phi. So my r 1, 0, I'm just going to put it together in all its glory. I'll remind you that rho is equal to 2zr over Na. So that's 2zr over Na. And because n is equal to 1, right, I can put that in there. I'm going to leave the z as plus 1. Or excuse me, I'm just going to leave the z as z. But we recognize that for hydrogen, z is equal to 1. Okay, so when I put that in, I've now got a 2 times the square root of z cubed, all divided by a cubed, times e to the negative rho divided by 2. Okay, and so follow with me here. If n is equal to 1, that means my rho is 2zr over a naught. But look, in the exponent, it's rho divided by 2. So that's going to cancel my 2. So that's now e to the negative zr divided by Bohr radius. And then now, so that was just my radial. Now I have to add my spherical harmonic, right? So I'm going to say this times now the square root of 1 over 4 pi. So now if I do some algebra on this thing, I know that I can pull out the, let's see here. Yes, I can pull out the 4 out of the square root, and that just becomes 2. Okay, so that's going to eliminate with this 2. Oops, we'll do a different color so you can see my algebraic manipulations. So that cancels with that. Lovely. And then now I can just put that pi into the square root, and I can write this function as the following. So that's going to be, let's see, square root of z cubed over pi a naught cubed e to the negative zr divided by a. Fantastic. I have this written somewhere else. I just want to make sure that, so I didn't write z cubed up here. Why did I not do that? I have to think about that for a moment here. I think that I might have a mistake on there that I've forgotten to do z cubed. Oops. Because you notice that's what I'm talking about in my Mathematica file, right? I forgot to put z cubed there. Okay, so we know it's not going to change it for, we know it's not, oops, retry. It's not going to change my result because for z equals 1, right, it doesn't matter. But let's put it in there to be complete. And there we have it, right? We've got our psi 1, 0, 0, which we know is our wave function for our 1s orbital. Very cool. And we can put together all of the other wave functions for 2s, 2p, 3s, etc. By calling up the correct radial wave functions and spherical harmonic wave functions. Sweet.